Hi everybody. So today we're going to talk about what is called variation of parameters. And variation of parameters is a way to solve non-homogeneous differential equations where what the non-homogeneous part is not predictable in the sense that the derivatives of this thing are not very predictable. What we've seen so far in looking at the method of undetermined coefficients is that the non-homogeneous part is something like e to the x, or maybe sine of x, or cosine of x, or a polynomial. And what I mean there is that the derivatives of all of those things are very, very predictable. Just to kind of emphasize this point, let me just show you this in Mathematica. I have a sheet here that I'm using Mathematica's manipulate command, where I am going to take derivatives of this function, e to the negative 2t. I'm going to take the derivative with respect to t, and I'm going to take the nth derivative where n can go from 0 up to 10 by ones. This is a nice little thing in Mathematica that allows you to kind of look at the way that a bunch of different things might end up looking. So this is the zero derivative, which is just the function e to the 2t. And every time I hit this plus sign, it's going to take the next derivative. So here's the first derivative of it, and the second, and the third, and the fourth, and the fifth, and the sixth, and the seventh. And what you see is a very predictable thing, that all of the derivatives end up having a coefficient times e to the negative 2t. Same thing would happen if I made it something like a sine of maybe 3t, and I started looking at all of the derivatives of that. You see that it's going to alternate between sine and cosine, and yeah, there's coefficients going on in the background, or that are coming out, but that's something that undetermined coefficients totally ends up taking care of. Even if it gets a little bit more complicated, something like maybe t times the sine of t, when we start looking at the derivatives of that, then you can see there's a t cosine sine of t, then there's a cosine t sine of t, and it kind of alternates back and forth between those two things. If it was something even more complicated, like maybe 2t times the cosine of 3t, then when I start looking at derivatives, you see that it's got four terms, but it always has four terms, and the four terms are always going to end up being the same. It's just the coefficients out front that are going to be different. So these kinds of examples are perfect for undetermined coefficients. When you get something that has derivatives that aren't predictable, like in my example, I was using the tangent. If we put in the tangent of t, then you'll see that we kind of create a mess, and we create it pretty quickly. The derivative of the tangent is the secant squared. Then I get secant squared tangent. Then there's the product rule up to the fourth derivative, fifth, and you can see that we're adding terms, and it's just becoming messier and messier and messier. There's no way for me to accurately predict what a really high derivative of the tangent is going to be. So that means that in a case like this, undetermined coefficients is totally not going to work. And that's what we have variation of parameters for. So here we are with variation of parameters. So I've got my differential equation in standard form, y double prime plus p of x y prime plus q of x y is equal to some function f of x. And then I'm saying that the complementary solutions are y1 and y2, and so all linear combinations of those. Again, I've got here that the x is the independent variable and y is the dependent variable. So we're going to use what's called variation of parameters in order to find a particular solution. This doesn't change. This only changes how we're finding the particular solution. Everything else about the way we did undetermined coefficients, where we used undetermined coefficients to find a particular solution and then put it together with the complementary solution, that's still going to be the same. We're just using a different method to find the particular solution. So what we're going to do is assume that the particular solution is some function times y1 plus some function times y2. This turns out to be a very reasonable assumption. This is not necessarily a linear combination. Up here, I have that C1 and C2 are always going to be constants. Down here, I'm saying, no, they're not always going to be constants. These are going to be some function of x. I can write virtually any function in this form. If y1 and y2 were maybe sine of x and cosine of x, and I knew that y of p was equal to x squared, I could let u2 be 0, and I could let y1 be x squared divided by the sine of x, so that the sine of x's would cancel, and I would end up with x squared. So I can really write any function in this form. And what I'm doing is saying, okay, well, let's say that it is in this form. I know what y1 and y2 are. If I can find u1 and u2, then I will have my particular solution. All right, so I'm going to take this and plug it into the original equation up here. So I take the derivative. It's a product. I'm going to stop writing the of x's. So the first times the derivative of the second, that's here, plus the second times the derivative of the first. Then I do the same product rule on the second term there. And then I go to do the second. Oh, and then I'm going to impose a condition. I'm going to grab onto this piece right here and this piece, and I'm going to say I want those things to be equal to 0. And you should really wonder why I'm allowed to do that. It's going to come back around towards the end. So make sure that you've got this written down, because that's going to be a key thing that we need moving forward. So if I put that the sum of those two things are equal to 0, then I'm only left with this first term and the third term. Right, so there they are, the first term and the third term. I'm going to take the second derivative. Again, my whole idea here is to plug it into the original function. Product rule. First times the derivative of the second, that's here, plus the second times the derivative of the first, and then I do the same thing with the second terms, and I end up with all of that. Remember, y1 and y2 are solutions to the complementary equation, so the homogeneous equation where we let f of x be equal to 0. So now I'm going to plug all of these things into this equation, and it's going to be kind of a big mess, so take advantage of the pause button here. So there I go. Here's the second derivative. Then I get times p, where p was a function, times the first derivative plus q times the original function, and then that's all got to be equal to f of x. What is not so obvious here, because that is kind of a big mess, which I'll point out with some colors, is that if you look at what is in blue, u1 times y1 double prime, u2 times y1 prime, or sorry, u1 times y1 prime, u1 times y1. If you take all of those blue ones together, you could factor out the u1, and then what you have is the homogeneous differential equation. Same thing with those red terms. I'll rearrange them. So I put all the blue ones together and factor out the u1. We started with the assumption that y1 double prime plus p times y1 prime plus q times y1 was equal to 0. So all of that stuff that's in blue goes away. Similarly, all the stuff that's in red goes away. And then I'm left with just this piece right here. So I need this piece to be true. I'm going to take that piece and put it together with the assumption that I made in the beginning, where I set those two things equal to 0. And I end up here with what is essentially a system of equations where I know what y1 and y2 are, and I don't know what u1 and u2 are, in order for me to figure out what those would be in order to get that equation.